Okay, so good afternoon, everyone. We're going to continue talking about hydraulic fracturing, and you have a new project to work on. It's I know I see some long faces that you may not like this, but most of the class here is consists on solving these weekly projects. So, and this one is not too long, okay? The second part is actually very short. The first part, it may take a little bit of time. But let me explain, first of all, what we are trying to solve over here. The first problem, probably I'm going to talk about that later on, but the second problem, it's about hydraulic fracture propagation. And it's a hydraulic fracture propagation model. That's exactly what we're going to discuss now in a few minutes. One of the objectives of hydraulic fracture propagation is to predict what would be the length of the fracture, the width of the fracture, and the pressure needed to propagate that fracture as a function of pressure, as a function of time. And in this example, we have a set of equations that we're going to show and derive today that show all these variables as a function of time for constant injection rate. So here, I is the injection rate, and it is constant. So it's basically that, and we're going to see that it's not too difficult actually to derive all these equations. Back in the days, usually in practice you will do just one hydraulic fracture and that was it. However, today with modern hydraulic fracturing, you do many of those fractures, and the question is, how close are you going to put those fractures? And actually opening the rock and the subsurface here, it's going to require some additional stress. And some additional stress on the face of the fracture is going to perturbate what is the local stress around the fracture. And that alteration of stress around the fracture can modify what is your local stress and what are your principal stresses. So for example, if your principal stress before fracturing was in this direction perpendicular to the fracturing, after fracturing on the face of the fracture, the minimum principal stress may not be in this direction anymore, because now you added stress in this direction in order to open that fracture. And how far that alteration of the stress go is something that you're going to solve in this problem. Probably I should switch the order of the problems. That will make a little bit more of sense. And in this case, what you're looking at here, it's so this axis X, this axis Y, this is a fracture that looks something like this. This is X. That should be Z. It's a fracture with a given height, which has propagated mostly in direction Z, and this is the height of the fracture. So what you're looking at right now, let me use some color for that. This line from here to over here is that line over there. And well, let me, probably now you see the color a little bit better. What this plot shows is what is the alteration of stress around the face of the fracture. And probably be easier if I use this as a visual aid. So your fracture is here, okay, and this is horizontal direction where the minimum principal stress was at the beginning. This is horizontal direction where the maximum stress was at the beginning. And your objective in this point is to calculate how far this stress reversal goes into the fracture. Okay? So just to help you also a little bit, if we look from the top, originally this one is SV, this one is SH max, and this one is SH min. And these red lines show what is the direction of SH max. And what they also show next to the fracture is that when you make this fracture and you alter the stress around this fracture, now the maximum stress is not in this direction as it is in the far field, but around here it is in this direction. Okay? I'll come back to this a little bit later, but basically what you're going to have to do in this case is you're going to have to go to FreeFEM and you're going to have to simulate if this is X, this is Y. Notice that in this example, you guys don't like FreeFEM? No? Okay, well next year I'll try to do the assignment in Phoenix. Not too different though, but it's the same concept.
I think the issue is a fundamental lack of understanding of what we're actually doing in FreeFEM versus just trying to blindly copy what you tell us to do in FreeFEM.
So, okay, probably we can discuss a little bit more about that on Tuesday. But what I like from FreeFEM is, to me, it's very clear what's going on. But if it's not very clear to you, probably we should discuss the code one more time in detail, because you can use that for a lot of things. And in this application, what you have to do is to simulate this same thing, but instead of simulating this fracture that it extends in vertical direction like this, extends in horizontal direction like this, and a cross section implying YX, it will be something like that. You have to simulate that fracture in YX with a half length, which is HF divided by 2, with a given width, which is given in the reference. And all the other properties are in the reference. So here, if you go, this is a paper from Professor Sharma some years ago, but my objective is that here you replicate exactly, well, almost exactly what they did in that paper. You'll see it's not too difficult. You need to calculate the alteration of stress in this direction, in this direction. That comes out from SXX and SYY. So right, this will be SXX, this will be SYY. And notice that this is in the vertical direction, this is in the horizontal direction, which was originally SH min. What you have to do here is to compute the alteration of stress in direction, in the other horizontal direction, which in this case is SZZ, which is going to be equal to this equation, because you're going to use a plane strain model. In their case, they use a 3D model, so they actually have a 3D volume of the fracture. In our case, we're going to assume this is just a plane strain solution, and this fracture repeats infinitely long in direction Z. And you're going to see that your results are not going to be too different from those from the reference. So basically, let me summarize. You make a fracture here with all the properties that are given in the reference. Don't add any far field stresses, okay? Just make all displacement 0 everywhere, pressure in the fracture, compute the change of stress in this direction, in that direction, and the change in the perpendicular direction is going to be given by this equation, Poisson ratio times the change of stresses in the other direction. you add that to the background stresses, and you will get to see how the new stresses compare to the old stresses. You just have to add the change of stress caused by the hydraulic fracture to the previous ones, and you will see that there can be a reversal of the principal stresses in this problem. For example, let me anticipate a little bit the results in this paper. I don't remember well the actual numbers, but the difference between SH max and SH min in this example is 100 psi. That means that if you had a pressure in your fracture which is higher than 100 psi, a net pressure higher than 100 psi, your minimum principal stress might not be your minimum principal stress anymore, because now it's 100 psi higher than what it was before. But in order to make these computations accurate, because also you're going to have a Poisson effect, you need to compute the stresses in this direction, in that direction, multiply those variations times the Poisson ratio, and that's going to give you the variation in the third direction. And there you will be able to compare those two. So I'll come back to this in a little bit, because actually we need to go through these models to see how those make stress vary around the fracture. But that's the objective, to do a computation of hydraulic fracture propagation, prediction of length, width, and pressure with time, and also to find what is the point in which the stress is reversed. Oh, one more thing from the practical point of view. Why do you want to know what is the point of the stress reversal? Any idea? Hamza? Because that will tell you where to put the second fracture, right? Because if you were to put the fracture over here, it won't grow in this direction. It will grow perpendicular to the minimum principal stress, but now the minimum principal stress is in this direction, so it's going to grow like that. So these calculations give you an idea about how close you can place your fractures. Ideally, you want to place them as close as possible to maximize surface area, but if you put them too close, they interfere with each other and they might not grow, or they might grow in some other directions in which you do not want them to grow. All right, so let's come back then now to the coupled fracture problem. And I believe that I didn't add this in the syllabus. Let me check again. But no, I didn't add this in the syllabus. But this part of the coupled fracture problem, you will find it in the book of Balco and Economides, and it's called Hydraulic Fracture Mechanics. It's a book from the 90s, and it explains the basic fundamentals of a single planar hydraulic fracture propagation. So, all right, let's continue on talking about this hydraulic fracture propagation. So, let me remind you a little bit about the geometry. If we have a hydraulic fracture that is limited by stiff boundaries, we're going to have the hydraulic fracture height, hydraulic fracture length, and the hydraulic fracture width if we do a cross section of that hydraulic fracture, right? So, in order to have this fracture open and propagating, we're going to see that we need some pressure in addition to the minimum principal stress. That's what is called the net pressure. And that net pressure is going to depend on many things. The first thing that we saw on Thursday, it was the pressure to create new surface, and that depends on the fracture toughness of the rock. We calculated this in class. Did you guys calculate the value of toughness? Anyone did it? For the experiment that we ran in class? No one? Okay, I'm going to give you a few minutes, a little bit later, not right now, okay? But you're going to find that these values of toughness, they vary around 0.1 and 1.5 MPa square root of meter, more or less, for rocks. But if you're opening a hydraulic fracture, you need to spend energy making that fracture. That's one component of the energy. A big part of that energy is just going to go into just opening the fracture. Even if you had a fracture that already propagated, and let's say it's a line fracture, in order to go from here to something open, you need energy, and the width of the fracture is going to be proportional. I hope that you see that it's going to be proportional to the net pressure, right? The more pressure you apply, the bigger the width is going to be, and it's going to be inversely proportional to, what do you think? What property of the rock is going to make harder the width to open? In this, let's consider in this case a fracture is not propagating. I'm just looking at the work needed to open the fracture. The stiffness of the rock, right? And in this case, we're going to work with some plane strain solution, so this is going to be the plane strain modulus. What the actual pressure that we need in order to open that fracture, we're going to see one particular case in a bit, but if you had a general pressure variation as a function of distance, if it's not constant, or if you had a three-dimensional fracture, you can solve this problem. Basically, this is just, and we assume elasticity, it's just elasticity, right? You solve this equation together with Cauchy's equation, and you don't have gravity, then that's going to be equal to 0. And the kinematic equations is all of that, and you will be able to predict that width. This is a relatively simple problem. It's just deformation. But you know how to solve this, and you're going to do it. You're going to solve this with free FEM too, right? For this simple case. But for any arbitrary shape or arbitrary pressure variation, you could solve this. This is just linear elasticity, and you know how to do it. The main concept here is that pressure, the higher the pressure, the bigger the width is going to be. And if you need a big width, then the pressure has to be higher, right? So that's one part of the problem. The other part of the problem here is that that fracture, in order to propagate, you need additional energy to make the fluid go from the wellbore through the fracture, right? We know these are fluids with some viscosity, so making them flow through the fracture, that's going to be that's going to depend on the properties of the fluid and on what else. If Qx is the flow rate, what is going to be the flow rate proportional to? What? Let's try to think a little bit about these equations before we actually go into writing lots of derivations. The flow rate is going to be proportional to, or inversionally proportional to, what? The width, very well. And the width actually is going to be very important. And the width, in this case, goes to the third. What else? Pressure, but specifically not pressure, but the gradient of pressure, right? So delta P, delta X, that's the higher the gradient, the higher the Q. And what am I missing here?
Area.
What?
Technically area.
Height. So we have width, and we also here we may have height. So there you have your area. What else? The viscosity, and it's going to go on the numerator or denominator? Denominator, right? So the more viscous the flow, the harder it's going to get for the fluid to go through the fracture. And we can also solve this problem. It's relatively not too difficult, especially if we assume a laminar fluid flow, and we assume that there is no velocity in the walls of the fracture. This is basically the problem of fluid flow between two parallel plates. And it's just a transport problem. And you know how to solve this. One more thing that is going to be important to consider in this case is that not all the fluid goes into the fracture. Well, all the fluid goes into the fracture, but not all the fluid stays in the fracture. We are dealing with porous media, and because of that, we're going to have what is called leak-off, right? So we're going to have leak-off, and not all the volume is going to go into the fracture. So last piece of the puzzle over here is going to be that remember that in order to propagate this fracture, we need to break the rock in this location, and that's going to depend on the fracture toughness. If the fracture intensity is higher than the fracture toughness, it will propagate. If it's not higher than that, it won't propagate. All right, so I think now we have all the elements that we need in order to solve this hydraulic fracture propagation model. Before we do that, let's try to go through the basics of fracture mechanics, and then we'll solve that problem. Okay, guys, how many of you are familiar with fracture mechanics? I know there is a course in fracture mechanics in mechanical engineering. No? Okay, so we're going to talk very basics about fracture mechanics, and this is almost everything you need to know for this simple hydraulic fracture propagation model. This is called the Griffith problem. And basically what Griffith tries to solve, he actually solved the problem, is what will be the stresses around a linear crack. So I have a fracture which is pressurized, and this is subjected to far field stresses sigma h, pressure inside the fracture P. The first thing that Griffith does is to simplify this problem. These will be the properties that we have in the subsurface, right? We have a far field stress and we have a pressure inside the fracture. This is equivalent to solve a problem in which we have the same linear crack, and this is just possible because we're assuming linear elasticity, with a pressure inside where that pressure is equal to the far field stress minus the pressure in the fracture, and this is what is called net pressure. So this is the name in hydraulic fracturing for the pressure in addition to the, there's a mistake there. Did you see a mistake, guys? A P is higher than sigma H. Otherwise, the fracture would not open. So, and that's what is called net pressure. Okay. So now let's try to solve this problem. And in order to do that, you raise your hand.
Yeah,
Lord?
what happens if you have an anisotropy in your far field stresses?
You will have to add this other stress in this direction, but actually that's not going to affect too much what we're going to do right now, because most of the variations are going to be perpendicular to this line. So let's put that into a coordinate system. So we're going to have this coordinate system where this is x, this is y. We have a linear crack, and I'm going to draw the crack as when it's already open. Okay, so when it's already open, as we're going to find from the Griffith solution, this is going to be an ellipse. This distance from here to here, we're going to call it C. As you can see from here, the half of the opening, or this vector over here, is going to be the displacement in direction y as a function of x. Somewhere over here on the wall of the fracture, I'm going to have a stress sigma yy, and the total opening of the fracture is what I'm going to call the width. So the idea here, let me add one more thing. This is opening because there is a pressure which is a function of x. The idea here now is to predict or to find equations for the displacement ui and for the stresses sigma yy around that fracture. All right, and in order to do that, what Griffith did was to assume a solid which is linear, which is elastic, which is isotropic, which is homogeneous. That means that properties do not vary in space. So many assumptions, right? But that's what we need in order to solve these equations. Okay, so we're not going to go to the work that Griffith did in order to solve this equation, because probably we'll have to do some convolution, like some nasty integrals that we're not going to go through. But I'm just going to give you the solution. If we have a pressure Px, which is a constant, Griffith shows that the displacement uy as function of x, it's going to be equal, and that displacement uy, we wanted to calculate it here at this position, initial position here, for y equal to 0. That's going to be equal to 2 times the pressure divided the constraint modulus times c squared minus x squared. So here's where the ellipse come from. You see, this is an equation of an ellipse, and this is going to be valid for x between 0 and what do you think is going to be here? And C, right? What is going to be the displacement after that point for C higher than C? 0, right? It's going to be equal to 0 for X, which is equal or higher than C. I notice over here too that if you put X equal to C, that's going to be equal to 0. And the maximum is going to be for X equal to 0. And from the maximum, already from this equation we get two things. One, this is an ellipse, and second, we can calculate the width. The width, the maximum width, when X is equal to 0, is just going to be 2 times this thing, and 2 times that thing is 4 times P0 C divided constraint modulus, where constraint modulus, as a reminder, anyone remembers what this is? It's a very important modulus. 1 minus Poisson ratio squared. Okay, so we have the solution now for this constant pressure crack, and we have the displacement. What about stresses? What is going to be the value of sigma yy, again, for y equal to 0?
That should be C, not 0. That's greater than this.
Thank you very much. C. What is going to be the value of sigma yy for, we're working with a non-porous solid right now. We'll change that later on, okay? But we're working with a non-porous solid right now. What is going to be the stress sigma yy at X less equal or smaller than C? Px, right? Everyone agrees with that? Which in this case, because it's a constant pressure, is just going to be P0. So just because of the reaction, if you apply a pressure P on the wall, the reaction has to be P. So everywhere inside the fracture, the pressure is just going to be P0. The non-trivial solution now is what is the stress for X bigger than C? What do you think is going to be? So somewhere over here. First of all, is this solid subjected to compression or to tension in direction YY? Compression, right? You're pushing, you're compressing. What about here? It has to be tension, right? Because all of this pressure that you're applying onto this boundary has to be counteracted by some tension that extends from here to there. So it is going to be a tension. And the equation for that is going to be P0 times, let's see if I can fit this in here, X divided square root of X squared minus C squared minus 1. Okay, so according now to this equation, I gave you the solution, so you have a solution in there. What is going to be the stress at the tip of the fracture for X slightly bigger than C? Y infinity, because this one tends to 0, right? This one tends to 0, and that's actually going to be, probably I should add a negative sign over here to show that that's tension. That's going to tend to infinity, and that's what the solution says. So if we were to make a plot somewhere over here as a function of x, but for sigma yy, you will see that as you approach to the tip, the stress sigma yy tends to infinity. Another useful quantity to know here is that in order to get to the value of tension but equal to the pressure inside the fracture, you need to get at the point which is at 15% higher than the value of the fracture half length. So you go to 1.15 C and you will recover this pressure but in tension. Okay? But it goes to infinity. That's what the solution says. Do you think that rocks have a can hold an infinite value of tension? No, right? However, we do have some cracks that they might not propagate even if you put some pressure on it. So this is what is called a singularity at this point. And we cannot deal with infinity. But what we can do is we can define a new quantity which is a finite quantity and something we can work with. And that's what is called the stress intensity factor. So in order to, we cannot compare this tension to a tensile strength. It's not possible because infinity is going to be always higher than the tensile strength. So instead of doing that is when we go to the concept of this stress intensity factor. And by definition, the stress intensity factor is going to be the limit when R tends to 0 from the right of, let's see if I remember this equation, the square root of 2 pi times R square root of that as well. Let's see, but don't copy, guys. I'm trying to remember the equation. I'm trying to force myself to remember this equation. So we'll see if it's correct. Times sigma yy as a function of R, where R is C plus R at 0. So let's see if it's correct. Yeah, it is correct, but it's just simpler to put all of this under the same square root sign. So R in this case is going to be this variable, is the distance from the tip towards further away from the tip. So I know you guys are here because you like math very much, right? I don't know if before in some course you had the opportunity to solve a limit with some practical application. I remember in calculus we solved limits all the time, but we never, after that we never did an example with limits. We did lots of examples with integrals, with Green theorem, things like that, but never with a limit. But this is the opportunity to do that. So I want you to tell me what is the stress intensity factor. Actually, I forgot to put the definition. This is Ki. I want you to tell me what is the stress intensity factor for a fracture which is pressurized at the constant pressure P0 with the length C. Okay? So you just have to put this sigma yy in there and take the limit as R tends to 0 from the right. I'll give you 5 minutes to solve that, okay? It's not too long. Hopefully you remember how to solve limits.
Should be possible.
What? You'll see it's not too difficult. Anyone doing some crazy trip during the Thanksgiving holiday?
Shopping.
No, shopping. Where's San Marcos?
Online.
Online. I don't know. I don't remember. You know how to do limits, but the idea is to take some terms into such a way that when you make that tend to 0, they will tend to 0 too, right? And in order to separate the variables that do not go to 0. So when you take the limit, all that stuff that tends to 0 disappears, but there's going to be something that will not disappear. In Thanksgiving, Georgina and I are going to be running experiments. Right?
Yeah, I'm running a lot of experiment right now. Last 3 days.
Okay, 3 days. No, but you don't have to come in the Thanksgiving. Don't worry.
That's why I'm happy my advisor's out of town.
Okay. So most of your experiments are in the field too, right?
Oh yeah. So I have data to analyze. I can just tell Stampede to run models and then go home.
Okay, how is that limit going? It looks like it says it's stress intensity. It's not intensify. It's intensity. So I can give you a hint. Obviously, constant. The pressure is going to be there, right? So this pressure, you can take it out. It's going to be somewhere over there. Anyone has a solution already? Did you guys ever solve a limit before for an application problem? I mean, we usually use it for derivatives and all that conceptual knowledge, right? But not for an actual application. I don't remember. I don't think I ever did a limit before for an application case. You have a solution? Min? That's pi?
Yeah.
Pi C. This looks. So this is mean solution. Let's see if everyone agrees with that. You got the same? cheating, Steve? You can use your phone to solve the limit, okay? Okay, guys. Well, I hope that you got, or you're on the way to the solution. This is correct. So the stress intensity factor for a constant pressure crack, it's proportional to the pressure. Makes a lot of sense. I was not the right one. So if you want to know how to get a solution, talk to me or talk to Min. She also got a solution, and I think Jamin also got it over there. So it's proportional to pressure. Makes a lot of sense. The more pressure you have, the more intensity you're going to have. But also very, very important is that it's proportional to length. The longer the length of the fracture for the same pressure, the bigger the stress intensity is going to be. What this means, and this is very important, is when you compare a given stress intensity to a given fracture toughness, KIC, which this is going to be constant for a given rock, or more or less constant. In order to propagate fractures, when they are short, it takes more pressure, it takes more work in order to break the rock at the beginning. But when fractures are already long, stress intensity very likely will be already higher than the fracture toughness. So long fractures are actually much easier to propagate than short fractures. So when they are short, you have to do all this work in order to propagate the fracture. But when they are long enough, even though if the rock is very tough, it's going to be very easy to propagate those fractures. So you're not going to spend much energy in propagating that fracture. I think we have everything we needed in here. One more thing that I'd like to highlight, it's let's see. No, I'm not going to go to this example because I think we're running a little bit out of time. But I'm just going to make another point. So the most important point from these analytical solutions, sometimes we know they're not going to be exact, right? But that's not the important thing. The important thing is understanding the physics here. First, about this intensity relationship with pressure and with length, and also for the width. Look at the width of the fracture. The width of the fracture has pressure in here and Young modulus in the denominator. And what that tells you is that the ratio of width to length is proportional to the ratio of pressure to Young modulus. So what do you think would be a reasonable net pressure in a fracture, more or less? You have something in mind? So usually, in situ stresses are in the orders of tens of MPAs. A reasonable net pressure is in the order of 1 MPa or a little bit more. Not more than that. 10 MPa maybe already quite a bit. But just remember, about 1 MPa, okay? What is the Young modulus of a typical rock? How much, Hamza?
More than 1 gigapascal.
Let's say 1 gigapascal, right? So 1 gigapascal is 1,000 megapascals. So 1 divided by 1,000, what this equation is telling you is that the slenderness of the fracture is about 1,002. The width is going to be 1,000th of the length. And that's very important to remember, because in all of these problems of fracture propagation in rock, where the rock is usually stiff, these fractures are going to be very slim. The width is much smaller than the length, and the ratio is about 1,000. Okay, so the same way that we were able to calculate a stress intensity factor for this constant pressure linear crack problem, we can also calculate that for the experiment that we run in class, right? Which was the tree bending test, in which you apply a pressure, well, actually you apply a force here. And we said that for that case, when the rock breaks, that's a maximum stress intensity that you can apply on it. This equation, which I think we already discussed before, is very similar to what we have written over there. And it depends on the notch, the length of the notch. And now this makes a lot of sense, right? The bigger the notch, the easier it's going to be to break this sample. And what am I missing here? I'm missing R. R is the radius. L is the thickness. And what else? What else? And I'm missing this coefficient that for it depends on I, A, R, and S, where S is the distance from here to here. It's about 5. So with a similar equation, we can calculate stress intensity for this test, and that's what's going to allow me. One of the ways, there are several ways to measure fracture toughness, is to measure fracture toughness of a material. All right. So let's put now all the theory together. I hope we have time. Let's see. Let me check. Yeah, I think we have enough. It will be 20 minutes to do this, so I think we're going to have time. We're going to write equations for a coupled hydraulic fracture propagation problem. This is what is called the PKN model, and I'm going to have to go a little bit fast, I think, in order to finish. It's called PKN because these are the initials of 3 guys that did a lot of work in hydraulic fracturing. And in this model, we're assuming that we have a fracture geometry that extends from the wellbore. This is a vertical wellbore. Extends from the wellbore with the shape of an ellipse. So here I'm just drawing one wing of the fracture. Far away, the width of the fracture is 0, so it's just a line. At the fracture is the highest. Already from here, and with this model, we assume there is a constant fracture height, HF. And if I'm looking just at one wing, this will be the fracture half length. And I'm going to assume plane stress solutions for this fracture as it propagates. So somewhere over here, the width is going to be smaller than in the wellbore. Somewhere over here will be a little bit, will be in between these two other cases. And somewhere over here is going to be thinner. So this is what is called a pseudo 3D model, because it is actually 3D, but it's solved with 2D equations. And those 2D equations, they are solved assuming plane strain perpendicular to the axis of the fracture, the center. So in this case, for example, you solve for stresses in this plane perpendicular to this. So this is the fracture for which you are solving. Before we get into the derivation of this, let me tell you that this fracture model, PKN, works whenever the fracture length is higher than the fracture height. There's going to be another model that solves the opposite case. We define HF, we define what is XF. I have to define here what the width will be. So the width of the fracture at the center of the fracture, that is what we're going to call W0 as a function of x, where x, coordinate x, starts somewhere over here. So our job now then is to solve in 3 dimensions, or actually it's going to be in 2 dimensions because we're going to use this simplification, of what is the pressure I need in order to open this fracture, and what is the gradient of pressure I need to flow fluid flow from here to there, where I want to know what is the pressure in the wellbore, assuming that the pressure at the tip is 0. So there is a gradient of pressure, and the fluid is flowing in the fracture, and at the same time that's opening a fracture. So with those assumptions, I can start writing some equations. From linear elasticity and a plane strain solution, as we have solved in just like a few minutes ago, the width of the fracture is 4 times the net pressure, but notice that now this net pressure depends on x, because this is flowing with time, times the fracture half length, which in this case is the fracture height divided by 2, divide plane strain modulus. And I can simplify this a little bit further to be like this. Okay? Nothing new so far. Fluid mechanics. We're going to write now the actual equation for the gradient of pressure. So the gradient of pressure as a function of x at the position x from the theory of flow between 2 parallel plates is going to be equal to this equation I'm writing right now, depends on viscosity. And okay, oh no, these are not parallel plates. This is flow through an ellipse, okay? To a conduit that has a shape of the ellipse, an ellipse, but it's very similar to the one of the parallel plates. So this is for an elliptical shape, Newtonian fluid. So viscosity is constant and laminar flow. Nothing new again. And the third equation is what it goes by material balance. And material balance, basically the injected fluid goes into 2 parts: the volume that stays in the fracture and the volume that leaks off. And this volume that leaks off, you can approximate it by some equations. For example, there is a famous one which is called the Carter equation, where, if I remember well, VL is 2 times the area of the fracture times the Carter coefficient square root of time, something like that. And the amount of injected volume, and we're going to assume this for this case, is a constant rate. So the amount of injected volume is just the injection rate times time. For this particular model, we assume this one to be constant. So, and this I is the injection rate. And this is just for one wing, okay? If you want the total for the 2 wings, you have to multiply that one by 2. All right, well, let's see, what do we do with these equations? We have to, I'm going to talk about leak-off later. I don't know if we're going to have time today, but you put now this equation and this equation into here, right? So let's see. I have a pressure here. I have a difference in pressure there. So let me put numbers to this. So this is equation 1. This is equation 2. And this is equation 3 and equation 4. So I can put together, look, the width is in the 2 equations, right? So I'm going to combine 1 and 3. And I'm going to put that width over there. Actually 1 and 2, not 1 and 3. And now I'm going to have that dp dx, I forgot about the sign, is equal to 64. The qx, what's going on, guys? Notice that qx is equal to I, okay? It's constant, and I'm assuming that there is no leak off. So actually this, let's call it equation number 5. So 1, 2, and also on 5, this takes me to this. Pi, I put the width from equation 1 in here, and this is 2 HF P net Q times HF. All right. So I just put the width in here and replace QX by I, assuming that there is no leak off. So I can simplify this a bit. You see there is an HF over there. I can simplify this a bit, and there are some numbers over here that I can cancel or divide or multiply. This young modulus, I put it in the numerator, and this is HF to the 4th, PNX to the 3rd. What can I do with this equation now? It's a simple differential equation, right? So when you want to solve for the, we would like to know what is the pressure in the wellbore. Okay, so what can I do with this? You can integrate, right? So the dP, notice the P, this P is going to go over here to the top from 0 to XF, and over here I integrate X from, wait. This is dP from 0. If I'm integrating in P, it shouldn't be XF, but it should be
Isn't it still
from P. Yeah. I didn't mean to erase that one. This one should be to P at the wellbore, right? So how do I call that one? Okay, so this is dp with the pn, and then I just have the variable x on the other side. So this is going to go from 0 to xf, 8 mu injection rate constraint modulus cube divided by pi, height of the fracture dx. And this one now, what is the integral of x to the third, power of third? You remember that? X to the power of fourth divided by 4, right? So this is going to be Pn at xf divided by 4 to the power of fourth minus Pn at x equal to 0 to the power of 4 divided by 4. But what was the net pressure at the end of the fracture? It was equal to 0. This was one of our assumptions, okay? And this is just an integral of 1, right? So it's just going to be x. So I'm going to save some space here and just write the constant part of this. Remember that hydraulic fracture height is constant. xf minus 0, so xf. All right? So notice that now we have an equation of the net pressure at the wellbore as a function of injection rate and length. So this is going to be mu I constraint modulus xf and since now we know what is the value of net pressure from equation number 1, that it's basically the width of the fracture as a function of pressure for a given section, we just can write that the width of the fracture is going to be equal to this divided by to the 1/4. So this one comes from, let me put, so we said this one was 5. So this one is equation 6. 6 plus equation number 1, where 1 was that one.
So that would actually be at specifically W naught x equals 0.
No, this is the width
Because
as a function of, let me think. Oh yeah, because this is the net pressure at x equal to 0.
Equals 0, and the other one's a function of P of n, function of f.
Very well, yes. And that's what my notes say also. Yes, thanks for the catching that. So yes, this is going to be the width at x equal to 0. All right, so with those equations, now we can do one more thing, and that thing is going to be, we would like to have all of these equations as a function of time instead as a function of fracture length. So the link through time is going to come from the material balance equation, from equation 4. Okay, So you can do some geometry, and you will find that the volume of one wing of the fracture is equal to the fracture half length times the fracture height times an average width, where the average width for that shape of this PKM fracture is pi over 5, this is just geometry, times the width at x equal to 0. All right? So we also know now from material balance, this is not from geometry, and assuming no leak off, that the volume of the fracture is the injection rate times time, which was actually equation number 4. So you combine this equation with this equation, and you will get that the fracture half length is going to be equal to the volume of the fracture, I times T, divided the fracture half length, the fracture height, I'm sorry, times pi over 5, the value that we just found here, right? And now you combine, you put this xf into these two equations, because now we know what is xf as a function of time, and you will get the final equations for the PKN model, where the fracture half length, this is just a number, it doesn't have any dimensions, is equal to this. We'll talk in a minute about the physical meaning of all these variables. The net pressure is this number, notice that it makes sense that time is in all of the equations. So don't worry if you don't get on time to write these equations, you have them in the page I gave you with the equations in there. So don't stress out about writing the equation. Okay. So put this one into the previous one, and then you get the final equations. And let's try to analyze what the equations tell us. First of all, it tells you that the fracture length for a constant injection rate is proportional to time. Makes sense, right? It's proportional to injection rate. Also makes sense. Inversely proportional to viscosity. I don't know if, that's a little bit more difficult to see. But it's inverse to that. We will talk about that in a minute. And it's inversely proportional to the fracture half length. And that makes sense, but this is just because of material balance. It means that for the same amount of injection, for a bigger fracture height, the length is going to be smaller because of material balance. I'll come back to these Young modulus in a bit. Let's see the net pressure. The net pressure is proportional to the constraint modulus, and this makes a lot of sense because the higher your Young modulus, the higher the pressure that you need for the same width for a fracture to open. The pressure is also proportional to viscosity, and that makes a lot of sense because you need to flow the fluid through the fracture. proportional to injection rate also makes sense because of the losses inside the fracture, viscous losses, and inversely proportional to the fracture height. And again, this is because material balance. And this increases with t to the 1/5. I don't remember if I have an example here, but I'll look for an example about that. But just, let me tell you before we get to there that a power up to the 4/5 means that this is more or less a linear relationship because 4/5 is about 1. But these two other ones, net pressure and the width, to the 1/5, they increase quickly at the beginning and they tend to plateau. Or not really plateau, but they increase much more slowly for bigger times. So this is about the net pressure, and for the width, it's proportional to the injection rate, inversely proportional to the viscosity of the fluid, inversely proportional to the constraint Young modulus, and this is again because of elasticity. The bigger the width, or the bigger the constraint Young modulus, the smaller the width is going to be. And the hydraulic fracture height, this is again because of material balance. For the same injection rate and a bigger hydraulic fracture height, you will have a smaller width. And let's come back over here. This dependence also is because of elasticity. What this means is that the bigger the constraint Young modulus, the smaller the width is going to be. And if the width is smaller, that means your fracture has to be longer in order to cover the same amount of injected volume. So these equations are all related, and now they take into account the elasticity part, and also the fluid the fluid flow in the fracture part, and they all interact with each other. Yes,
I
John.
don't know if I heard this correctly, but earlier you had said that XF doesn't have units.
No. I meant these coefficients. Yeah, these coefficients are some, like pi divided by 16, stuff like that.
Okay.
But
XF is at the actual length of the.
yes. So when you solve this problem, and actually this is problem number 2, I strongly recommend, I'm giving you numbers in field units, but I strongly recommend that you convert all of those numbers to SI units before putting them in these equations, because otherwise it's going to be a big pain to convert those field units to just to work everything in field units. And remember, these are just numbers. These are just coefficients. If you put everything in here in field units, here you will get meters, pascals, meters. And then you can convert that back to whatever you want. All right, so let's see how we are doing with time. Well, we're over time. Sorry about that, guys. But work on the second problem. It's very easy. It'll take you half an hour. The other one, it will take a little bit more, but we'll talk more about that on Tuesday. Okay? All right, guys. Happy Thanksgiving. I'll see you next week.